Garments are one of the most common type of object in our life, yet they pose a set of unique properties that make them incredibly difficult for machines to perceive and interact. First, with a near infinite degree of freedom, a garment's full configuration is often described by the per-vertex 3D locations of its entire 3D surface. However, garments are also commonly subject to extreme cases of self-occlusion, especially when folded or crumpled, making it challenging to perceive their full 3D surface. Moreover, garments usually consist of thin surfaces that is not watertight. This unique geometric property makes them ill-suited for typical 3D representations designed for solid, rigid objects, such as truncated sign distance function or occupancy grid. To address these challenges, we present GarmentNets, a category-level post-estimation framework for garments. The key idea is to formulate the deformable object post-estimation problem as a shape completion task in the canonical space. By mapping the observed points to the canonical space, we estimated the pose for all observed surfaces. By completing the shape in the canonical space, we estimated the pose for all unobserved surfaces. This canonical space is defined across garment instances within the category, therefore specifies the shared category-level pose. To obtain input, the robot will lift the garment up by gripping an arbitrary point. After that, 4 RGBD images were taken, which is then fused and downsampled into an unordered RGB point cloud. After obtaining the input, our framework predicts the full geometry and pose of the garments in 3 steps. In step 1, we use a PointNet++ style network to predict per point canonical coordinate. By doing so, we predicted the pose for all observed points. The associated features for each point is scattered into a sparse feature volume using their predicted canonical coordinates. The sparse feature volume is transformed into a dense feature volume using a 3D convolutional neural network for later stages. Here is a visualization of the predicted per point canonical coordinate. Step 2 is shape completion in a canonical space. Here, we predicted an implicit neural winding number field using features interpolated from the dense feature volume. The winding number field equals 1 on the inside of the garment and 0 for the outside. Across an actual surface, the winding number jumps sharply from 0 to 1. Across a hole, however, the winding number transitions from 0 to 1 gradually. Using this unique property, the holes of the garment is represented using the magnitude of gradient. Comparing to commonly used representations such as truncated sign distance function or occupancy grid, our winding number field representation is able to capture both the thin surface of the garment as well as holes such as the front opening of a jacket. In step 3, we finally estimate the full pose of the completed garment by predicting a neural implicit warp field back to the observed pose. The completed garment is extracted from the winding number field using a slightly modified marching cubes algorithm. Here is a visualization for the predicted warp field. Since the warp field is evaluated for every mesh vertex, we can maintain the per point correspondence back to the canonical space, which is useful for many downstream tasks. In summary, we address the near infinite degree of freedom by defining a category-level canonical coordinate space. We address a problem of severe self-occlusion by formulating the post-estimation problem as a shape completion in a canonical space. Finally, we address the garment geometry of thin structures with holes by a novel winding number field representation. We tested our algorithm on input generated by physics simulation. We also tested our algorithm on some real-world garments. The point cloud is captured using an iPhone 12 Pro. Thank you for watching. Please check out our paper for more details.